Hi all, welcome to Physio Exam Buddy. This video is related to the pressure changes happening in the cardiac chambers as well as in the blood vessels during a cardiac cycle. The pressure changes in these cardiac chambers as well as blood vessels, it is usually measured by cardiac catheterization. We will see first the pressure changes in the cardiac chambers. First about the pressure changes in the atria. Hope you all are thorough with the Vigor's diagram from the first video. So, during atrial systole, what happens to the pressure in the atria? So, this left atrial pressure, it is represented by the blue line in this diagram. During atrial systole, the right atrial, this is the atrial systole, the right atrial pressure, it increases from 4 to 6 millimeters of mercury. Here, the changes in the pressure from 0 to 120 millimeters of mercury is marked. So, you can see here that the pressure change occurs only up to 4 to 6 millimeters of mercury in the right atrium during the atrial systole. And left atrial pressure, it increases from 7 to 8 millimeters of mercury during atrial systole. During the isovolumetric contraction phase, that is after the atrial systole, it is followed by the ventricular systole, and the first phase is the isovolumetric contraction phase. And during the isovolumetric contraction, the atrioventricular valve, it will bulges into the atria, which will further increases the atrial pressure. So that is why you can see a slight slope in the isovolumetric contraction phase. And after this, during the ejection phase, the AV valves will be pulled down by the contracting ventricles, and this will increases the atrial volume and decreases the atrial pressure. Next, we will see what happens during the atrial diastolic phase. During atrial diastole, this is the atrial diastolic phase. So, it actually coincides with the complete of the ventricular systole as well as the initial part of the ventricular diastole. So, during atrial systole, the atria is getting filled with the blood from the major veins, while the AV valves are in a closed state. And this will lead to a rise in the intra-atrial pressure, which becomes maximum just before the opening of the ALP valve, and that is corresponding to the end of the isovolumetric relaxation phase. So you can see here that this is the atrial diastolic phase. So during this phase, the atria get filled with the blood from the veins, and the AV valves is in a closed state. So you can see here that the intra-atrial pressure rises and it become maximum just before the opening of the AV valve. So AVO, it represents AV valve opening, which occurs at the end of the isovolumetric relaxation phase. And after that, what happens? After the opening of the atrioventricular valves, the atrial pressure is found to be decreased. So that is about the pressure changes happening in the atria during cardiac cycle. This pressure changes in the atria is not complete without explaining the jugular venous pressure. So, the atrial pressure changes, it can be studied by studying the pressure changes in the right internal jugular vein. The reason for this is the right internal jugular vein is in direct communication with the right atria, and the pressure changes in the atria are transmitted to the internal jugular vein. And another reason is that there is no valves in the internal jugular vein, and the midpoint of the right atrium lies approximately 5 centimeters below the sternal angle, with an average pressure of less than 8 millimeters of mercury. So these are the reasons why the pressure changes is reflected in the right internal jugular vein from the atrium. This jugular venous pulse, it is represented in this left atrial pressure. So this venous pulse has three positive waves, that is A wave, C wave as well as V wave, and two negative waves or descent, which is the X descent as well as the Y descent. This A wave, which is happening during the atrial systole, is the first positive wave in JVP, followed by C wave, which is the next positive wave. And the C wave, it is because of the bulging of the atrioventricular valves into the atria during the isovolumetric contraction phase. So you have to draw the C wave corresponding to the isovolumetric contraction phase. This causes an increase in the intraatrial pressure, which is transmitted to the right internal jugular vein, which is reflecting as a positive C wave. Next, during the ejection phase, that is during the ventricular ejection, AV valve will be pulled down by the enlarging atrial cavity. So this will reduce the pressure in the atria, causing the X descent in the JVP during the ejection phase. Followed by the X descent. Next is the V wave. V wave results from the rise in the atrial pressure due to the slow flow of blood into the atria through the veins, while the AV valves are in a closed state, and this continues up to the end of the isovolumetric relaxation phase till the AV valves become open. And once these AV valves are open, it will cause the blood to flow from the atria into the ventricles, reducing the atrial pressure. So that is the one which is responsible for the decrease in pressure, showing as Y descent in the JVP. Next, a few words about the abnormalities in the JVP, which can be asked as an MCQ as well as in practical viva questions. A wave in JVP is prominent in conditions like pulmonary stenosis or pulmonary hypertension. And you can get giant A wave or cannon waves in complete heart block. And this A wave will be absent in case of atrial fibrillation, and you will get a giant C wave in case of tricuspid insufficiency. Next is about the pressure changes in the ventricle. We have finished with the pressure changes in the atria. Now we are moving on to the pressure changes in the ventricles. And first of all, we will see the left ventricular pressure changes. Again, so this is the left ventricular pressure, that is red colored line in this Vickers diagram. During atrial systole, you can see a small rise in the pressure as seen in the left ventricle. But what happens at the end of the atrial systole? The left ventricular pressure, it actually decreases to around 1 to 3 millimeters of mercury. So the pressure you can see here that it is marked from 0 to 120. So at the end of the atrial systole, the left ventricular pressure, it actually decreases to 1 to 3 millimeters. So you have to draw it like that, corresponding to 1 to 3 millimeters of mercury. And what happens in this isovolumetric contraction phase? During isovolumetric contraction, the ventricle contracts as a closed chamber. So the intraventricular pressure will rises up to 80 millimeters of mercury. So you can see here at the end of the isovolumetric contraction, the pressure in the left ventricle, it is around 80 millimeters of mercury. And when this intraventricular pressure rises above 80 millimeters of mercury, our semilunar valves will open and blood will be ejected into the aorta, and the left ventricular pressure reaches a maximum of around 120 millimeters of mercury. Now, what happens during the reduced ejection phase? During this reduced ejection phase, you can see here that the intraventricular pressure, it starts declining. So that is why this decline in the red line. Then the next phase is the of the ventricular diastole is the protodiastole, and during this phase the ventricle starts relaxing and the intraventricular pressure decreases further. And when the intraventricular pressure decreases or it is less than the pressure in the aorta, there is a tendency for the blood to backflow from the aorta into the ventricles, and it is responsible for the closure of the semilunar valves, which is happening at the end of the protodiastole. And the protodiastole, it is followed by the isovolumetric relaxation phase. And in this isovolumetric relaxation phase, you can see here that the left ventricle relaxes without any change in the volume, and there is a steep fall in the pressure from about 80 millimeters of mercury to nearly 0 millimeters of mercury. And when the ventricular pressure falls below the left atrial pressure, our AV valves will open. During the rapid filling phase also, the pressure in the ventricle, it is low due to the continuous relaxation of the ventricle, and the minimum pressure of the left ventricle, it is 0 to 5 millimeters of mercury. Next is about the pressure changes in the right ventricle. All the changes in the right ventricle are similar to that of the left ventricle, except that the pulmonary valve here open when the ventricular pressure exceeds 10 millimeters of mercury. And next one is that the peak pressure reached during the rapid ejection phase, it is only up to 25 millimeters of mercury. And the minimum pressure reached during the diastole, it will be 0 to 3 millimeters of mercury in case of right ventricle, whereas the minimum pressure reached is 0 to 5 millimeters in case of left ventricle. Pressure changes in the aorta. You can see here that this light yellow green color, that is the one which shows the aortic pressure changes, and you can see here that it only varies between 80 to 120 millimeters of mercury. At the start of the ventricular diastole, this atrial systole first phase is corresponding to the last phase of the ventricular diastole. So during the ventricular diastole, you can see here that the aortic pressure, it is 80 millimeters of mercury, and it is because of the elastic recoil of the arteries maintains a high pressure in the arteries even during diastole because of the Wien-Kessel effect. And no change in the aortic pressure during the atrial systole as well as the isovolumetric contraction phase. So during the atrial systole as well as during the isovolumetric contraction phase, there is no change in the aortic pressure. That is, it is maintained only up to the 80 millimeters of mercury. Now, what happens at the end of the isovolumetric contraction? You can see here the ventricular pressure will exceed the diastolic pressure in the aorta, and our semilunar valves will open at the end of the isovolumetric contraction phase. And in the now you can see here that in the rapid ejection phase, this is the rapid ejection phase, the blood is ejected into the aorta. So the aortic pressure rises and reaches a peak of about 120 millimeters of mercury during the rapid ejection phase. And this will be followed by the reduced ejection phase, where the ventricle will be pumping less forcibly, so pumping less blood. So since the inflow of the blood into the aorta is less than that of the peripheral runoff, the aortic pressure should fall in the reduced ejection phase. Now, in the late part of the ventricular systole, the aortic pressure actually exceeds the ventricular pressure, but only for a very short period because the momentum will keep the blood moving forward. And during the ventricular diastolic phase, you can see here that the ventricular pressure falls. That is, when the aortic pressure exceeds the pressure in the left ventricle, there is a tendency for the backflow of the blood in the aorta, which will be halted by the closure of our semilunar valves. And you can see here that a small depression or notch called incisura will appear in this aortic pressure curve, and the sharp closure of the aortic valve causes a momentary rise here in the aortic pressure because of the sudden cessation of the backflow of the blood. And next, the pressure in the aorta is again maintained at 80 millimeters of mercury during the rest of the diastole. So you can see here the pressure in the aorta is maintained at 80 millimeters of mercury during the rest of the diastole. Next is about the pressure changes happening in the pulmonary artery. It is similar to that of the aortic changes, but here the systolic pressure is only 25 millimeters of mercury and the diastolic pressure maximum it will reach only up to 10 millimeters of mercury. Next is about the ventricular volume changes. So here this pink line, that is the one which is representing the ventricular volume changes in the Vickers diagram. You can see here what in the atrial systole there is a slight abrupt increase in the ventricular volume, and this is 130 ml. The maximum end diastolic volume it is around 130 ml, and you can see no change in the volume on the ventricular volume during the isovolumetric contraction phase. But after isovolumetric contraction phase, there is a large reduction in the volume during the rapid ejection phase, as well as a smaller reduction in the volume during the reduced ejection phase. Thus, 70 to 90 ml of the blood is ejected by each ventricle into their corresponding arteries during each beat, and you can see here at the end systolic volume. The end systolic volume it is around 50 ml, and there will be no change in the volume, ventricular volume during the isovolumetric relaxation phase. After that, there is a large increase in the volume during the first rapid filling phase and a smaller increase in the volume during the diastasis phase. So that is about the pressure as well as volume changes in the cardiac cycle. Again, you have to draw the same Vickers diagram when the pressure as well as when volume changes are asked in the cardiac cycle. Thank you.